And welcome to part 2 of electric circuits. When we left off, we had learned Ohm's law and the power relationship. And now we're going to take a look at series. Different types of circuits. There's 2 types of circuits, series and parallel. To be in series, there has to be a long string of them, there has to be a string of them, 2 or more, and it has to be a one-way string. Now I can loop around and curve, that's okay. But there has to be only one direction you can go. If it splits so that you have a T, so that you can pick a direction to go, it is no longer in series. So this circuit here is in series because you start with the battery to B, you go up and over to R1, you have no choice, you have to keep going to R2, then to R3, then to R4, and then back to the battery in that full loop, and there's nowhere else to go. Since there's nowhere else to go, that is in series. And as long as there's nowhere else to go, there's only one direction straight ahead, you are in series. Now in series, we have to take a look at the current and the resistance and the voltage. Those are the 3 things we need to look at. Most of them stem from this equation here. Now this equation has 2 uses. It can be used for the entire circuit. So that means the voltage for the circuit equals the current for the circuit times the effective resistance of the circuit. And this also applies to parallel circuits. Or you can do it for a component. The voltage of some component, let's say R4, equals the current that goes through R4 times the resistance of R4, the value of R4. Now, how do we get that? Well, in series, one of them is pretty straightforward, the current. So the current is a constant in a series circuit. Why? Well, let's imagine water flowing through a loop. Well, that water has to keep going because it can't build up. Because if it builds up somewhere, then it just stays there and there's nowhere else for it to go, and it just builds into a big pool. That's not going to happen in this circuit. We're not going to pool our energy. There's no battery, no capacitor to do so. Resistors don't collect energy. Energy passes through them. So the rate the energy passes into the resistor has to be the same as the energy rate passes out of the resistor. It can't keep the energy. And so that current all the way across the circuit has to be the same. Because everywhere there's energy in and energy out have to be the same. So R1, R2, R3, R4, and V all have the same current. So that means that if I take the effective resistance of the circuit times the current, the effective current for the circuit, that equals the voltage of the circuit, which is going to be, in this case, equal to the voltage of the battery. Now, how do we get the effective resistance? Well, in series, it's like doing an obstacle course. And you have to do obstacles one at a time. Well, each obstacle that you do makes the course more difficult. And of course, the more difficult each obstacle is, the more difficult it is total. So what you do is, for the effective resistance, is you just add up all the resistances that you encounter along your way. So R effective equals R1 plus R2 plus ... until you get to the last resistor. You just add them all together. So if I have 4 resistors, it's R1 plus R2 plus R3 plus R4. If I only have 2 resistors, it's R1 plus R2. If I have 10 resistors, I just add up all 10 resistors. So for those who like more fancy math, it's the sum of all resistors. All resistors on the series circuits. There's hybrid circuits too. We won't get into those much for this class. So that means that the current is equal to the voltage, the total voltage for the circuit, which is the voltage for the battery, divided by the effective resistance. All right, so let's have a circuit with 3 resistors, 4, 3, and 9. What's the effective resistance of the circuit? Hopefully you don't even need to grab your calculator, do the math, and hopefully you're done. R effective is equal to R1 plus R2 plus R3, which is 4 plus 3 plus 9, which equals 16. So my effective resistance is 16. By the way, 16 equals futile. I don't know why. No, Star Trek jokes. We get it, the board. Okay. In parallel. In parallel is a little bit different. And again, we're going to use the water analogy. Imagine I have a river, and every dam and whatever, rapids and what, those are like resistors in series. But at some point, oftentimes the river will split. It'll split from one part here and come back together on the other side of that island up there. So in between those 2 points, the circuit is called to be in parallel because I have 2 parallel branches moving from point A to point B. So I have one split, everything moves and then comes back together again. Each of the splits are called nodes. Nodes are points that you see in the dots there where I get a choice between coming in from part A and go B or C. So I can go to R2 or I can go down to R1. And so that is a node, it's a split, and they both come back to the bottom top there with no other splits. If there's any additional splits, I'm no longer in parallel. I now have a hybrid circuit where I have parts that are in series and parts that are parallel, and those are very complicated, too complicated for this particular class. So we will focus on series or parallel. All right. If this was a 200 level physics course, we would do both, we would do hybrids, and then you would solve it. You would find some part that's either in series or parallel, solve it, draw in the effective circuit, and then solve the next part. Usually what happens is you go back and forth between series and parallel, series and parallel, series and parallel, and you get to play what's called the physics chutes and ladders, otherwise known as Kirchhoff's laws, but that's beyond this class. So I have a current. This is the total current, the effective current of the circuit. And when it hits this node, it splits. Some of the current goes here, and some of the current goes here. The current is no longer a constant, because some current will go this way, some current's going to go that way. Since my current has a choice, it's a little bit easier to move my current. Therefore, the effective resistance is lower. So that the resistance of the entire circuit is now lower than any of the resistors in the circuit. Before, when they were in series, the resistance, the effective resistance, was higher than all the resistors because it was harder to go from A to B to C to D. But in this case, I opened a new lane, and so some cars can go that way, and it makes it the traffic a little bit easier to manage. And so the resistance goes down. So in this case, instead of adding up the resistances, and by the way, voltage component always equals current times resistance component. Notice I didn't put current component because in series the currents are all the same. So I don't have to worry about that, just whatever the effective current is, where the effective current was equal to the voltage for the circuit divided by the resistance for the circuit. So maybe I should write that down. I equals voltage total over, so the battery voltage divided by R effective. All right, in parallel, the 1 over the effective resistance is equal to 1 over R1 plus 1 over R2. And if I have a third one going into this one, and out of this one and into this one, so I have 3 branches instead of 2, then I'm going to do plus 1 over R3 plus 1 over R4 plus 1 over 5, etc., etc. Now please note at the end you're going to get 1 over R effective, so you have to invert it. A lot of people forget to invert it. Also, there is a math trick. If you only have 2 resistances, I'll show you the math. If you get the denominator the same, you can add them together. So I'm going to multiply this by R2 over R2, so it stays the same. And this one R1 over R1. So I have R1, R2, R1, R2. So this equals R2 plus R1 over R2 times R1 equals 1 over R effective. Now, if I invert both sides, you can do the same math. You can do whatever math you want, just as long as you do it equally to all sides. Math is the most politically correct thing in the universe. Okay, that gives me R effective equals R1 times R2 divided by R1 plus R2. In fact, this is a math trick that works not just in this case, but there's a lot of other cases in physics where this works as well. So here it is down here. Now, that gives me the effective resistance. Now, how do I calculate the current? This one's a little bit trickier. Before we do that, let's do a quick sample though to get the effective resistance, because we're going to have to calculate the effective resistance in order to get the current. Okay. So suppose we have two resistors. R1 is 5 ohms, R2 is 10 ohms. What's the effective resistance? Go ahead and calculate that out. Go. And hopefully you're done. Five times 10 over 5 plus 10, which is 50 over 15. 50 over 15 is 3.3 ohms. So notice that this is lower than the lowest of the two. If you get a number that's bigger than any of your resistances, then you know you did something incorrect. Okay, so that's my effective resistance. All right, now what about the current? How much current do I have through R1 and how much current do I have through R2? Actually, it turns out I don't need to know the effective resistance to do that, but it can kind of help. First, let's do the current for the entire circuit. That one's a little bit more straightforward. How much current do I have flowing through the circuit in this particular scenario? Well, I do voltage equals current times resistance. So current equals voltage over resistance. Now, let's say my voltage is 8 volts, just to give a number. I haven't given it, so let's say it's 8 volts. I'm just making up a number. Divided by 3.3 ohms, and I do my math, and I get about 4.1 amps. Or sorry, no, that's not right. Oh, that's not even close to right. I inverted it. I did 33 over 8. I don't know why I did that. This is going to be 2.1.4 divided by 3.3 less than half, 2.4 amps. Now I'm rounding the heck out of it. Okay. So that's my amperage. Now that's the amperage that goes through the battery. Now how much of that is going to go through each of these? Now I've kind of hinted at something by saying how much of that is going to go through each of these. Because what happens is this current is going to split. Some of the current's going to go here, and some of the current's going to go there. So how do I determine how much goes across? Well, in series, the current is the same. In parallel, the voltage is the same. The voltage for each branch, that is. Now, why is this? Well, remind yourselves that voltage is the electric height. I go from ground at the bottom here, that's voltage 0. So this here is all voltage 0, because my wire is going to have effectively no voltage, almost no voltage, 0.0001. And I go through my battery. So I'm now at 8 volts up here. So I've gone from the ground to 8 volts. Now I have two choices about where I can go. I can go this way, or I can go this way. This way is a hill that's kind of a long, rounded curve that goes a long ways and circles around, and that's why it's a high resistance. The other way just goes straight down the hill, so it has a very low resistance. All right. Now, which one will have the greater voltage drop across it? R1 or R2? Hopefully you've thought about that a bit. Now let's consider this. What's my voltage here? And what's my voltage there? They both go from the same place to the same place. From the same place to the same place. They go from the top of the hill to the bottom of the hill. Just one goes very directly, one kind of goes in a roundabout way. But the change in height in both paths is the same. Since the change in height is the same, that means the voltage drop is the same. So voltage goes up through batteries and down through resistors, usually. So I go from 8 to 0, that means my voltage drop across R1 and R2 is both 8 volts. So I'm going to call voltage 1 and voltage 2, they both equal 8 volts in this case. So if I want to get my current, I set my voltage equal to current times resistance, because the voltage for a component equals the current through that component times the resistance of that component. So that means the current 1 equals voltage 1 over resistance 1. Current total equals voltage total over resistance total. Current 1 equals voltage 1 over resistance 1. Current 2 equals voltage 2 over resistance 2. And now I just plug in the numbers. 8 volts, 8 volts. This was 5 ohms. This was 10 ohms. So this is 1.6 amps, 0.8 amps. Now, I want you to do something real quick. I want you to add up I1 plus I2. 1.6 plus 0.8, what does that give us? No, it doesn't give us 4.7. It gives us 2.4. No, it was your cat that said 4.7. I don't know why you watch this with your cats. 2.4. Now, where else did we have 2.4? Right there. So that means that the current that goes into this dot is 2.4. The current that goes out of the dot is also 2.4. It's just that I split my 2.4 to 1.6, or sorry, 1.6 and 0.8. So current in always equals current out of a node. That's very useful if you're doing the trig-based class. We don't do as much of that here, but it is a good thing to note because it's a pretty straightforward concept. All right. I think we've covered all this, but if you want a refresher, here it is. And now we can move on. Okay, so what happens if you have too much current in some part of a circuit? So now why do we use series and parallel? We use these types of parts of circuits because they allow us to regulate the current that goes to different parts of our device. There are some parts of the device that 1 amp would be so much that it would just fry it instantly. There are some devices where 1 amp is simply not enough juice. It won't run correctly. And so we need to have different parts of the device that have different currents. And we do that by doing things in series and in parallel. We put them together, we call it hybrid. And that allows us to have different currents for different parts of the circuit. Use resistance if you want the current to be lower. Use parallel if you want the current to be higher. Now, what about into your house? How do you prevent there being too much current going into your house? Because that could be very dangerous. That could burn down your house and potentially kill you. So how do we prevent that? Well, there's two ways to do that from a large perspective. The first way is through a fuse. Now, a fuse is a strip of wire or metal that if the current gets too high, it'll heat up the wire enough that it'll break the wire and thus break the circuit, so that you can't get over that amount of current. It gives you a maximum limit to the current. That's called a fuse. So a 20 amp fuse will break if the current gets above 20 amps. So you can never get above 20 amps if you have 20 amp fuse in your circuit. This will kill the circuit and kill the current, because now your resistance goes to infinite. Back in the day, long time ago, houses used fuse boxes and fuses, which means that if your fuse went out late at night, you had to go down in the dark with a flashlight and replace the fuse in the fuse box, which clearly is kind of dangerous because you're putting two wires in a circuit that may still be broken. You may not have fixed the problem, and it may just break again with you in the middle of it. So that was kind of dangerous and expensive, and you had to replace it each time. And fuses are not cheap. And if you didn't have a fuse, you had to go down to the store and hope they were open. And back in those days, at night they're probably won't, so you pretty much have to spend the entire night without electricity or heat. You didn't have that good stuff. So what we do in the modern days, we use a circuit breaker. Circuit breakers occur, the basics of this is that if the current gets too high, it pushes the two wires apart and then breaks the current, the circuit. And all you have to do is snap it back into place and your current readjusts. But when this happens, make sure you fix the problem first, otherwise it'll just do that again, or maybe worse. So if your microwave shorts and sets off the circuit breaker, before you put it back, you might want to unplug your microwave or figure out what's wrong with the microwave. Or in this case, if it's shorted, you're pretty much going to have to replace the microwave, and they're not that expensive. I like to buy mine at auction for $2 a piece. So you get paid for it. But then you don't have to replace the circuit. You just go downstairs with your flashlight, you flip the switch, and that's all. Plus, it's easy because if you want to just turn off the power to fix something, you just flip the switch and then you flip it back on. With the circuit, with the fuse box, you'd have to take out the fuse and put it back in. A little bit more fuse. All right, this leads us to transformers. We're going to talk about transformers again later. Transformers are actually more with magnetic fields, and they'll actually be with the test on magnetic fields, which is the final exam. There might be a little bit on them on the third exam, but not a whole lot. And they're pretty straightforward, so they're not so bad. Now, what transformers do is they transform one voltage to another. Simple as that. Say you need a 100 volts instead of 50 volts. Well, you put in a transformer that would transform your voltage from 50 to 100. The boxes I told you about that convert alternating current to direct current can also adjust the voltage as well, because sometimes you need a smaller voltage. You may need 8 volts instead of 120. They can do that as well. So they can change from alternating current to direct current. They can also change the voltage. So a lot of times you have a transformer as well. Now, why would we want to change voltages? Well, it turns out the power loss along the power line depends on the voltage. Actually, inversely on the voltage. The higher the voltage, the lower the loss. So if you have a very high voltage and send it for a long distance, you lose a lot less energy. If you have a low voltage, you lose the energy very quickly. And so what electric companies do is they send voltage on very high voltage levels across the lines for hundreds of miles until they get to the city, and then they start to ramp the voltage down into the residential areas, and then they ramp it down going into your house using a series of transformers. Which is why a lot of times your electric goes out, it's because a transformer blew, and then they have to replace the transformer. And you can't fix transformers, you have to replace the other things. So they go from 100,000 volts to 120 volts. Now, energy must be conserved. Energy must be conserved. Power is energy per time. That means that power is also conserved. So that means the power that goes into the transformer has to be the same as the power that goes out of the transformer. So power 1 equals power 2. I didn't write that. Oh, I did write that. Well, so like I say, transformers are really straightforward. So if I tell you what the power is on side 1, you already know what the power is on side 2. A lot of people will spend 30 minutes trying to calculate it by using the voltage and current, and calculating it using this. But the reality is that all you have to do is use this equation here. Happens a lot. And if it happens to you, don't worry. That just means you're in the majority. All right. Now, the transformer is based on loops. Each side of the transformer has a number of loops. Each loop has a specific amount of voltage. A little bit more on this when we talk about magnetic fields. So that means that the voltage on the first side and the voltage on the second side is equal to the ratio of the loops. N is the number of loops. So N1 over N2 is the same as voltage 1 over voltage 2. So if you have 3 times more loops, you have 3 times more voltage. Or if you want to do V2 over V1 equals N2 over N1, doesn't matter which way you go. Now, power equals current times voltage. Since the power is the same, that means I1 V1 equals I2 V2. If I solve for I1, that means that I1 over I2 is equal to V2 over V1, so they're inversely related. Voltage and current are inversely related. That means if my voltage goes up, my current has to go down. If my voltage goes down, my current has to go up. So that means that the ratio of the currents is inverse of the ratio of loops. If I have 3 times more loops, I have 3 times less current. If I have 3 times less loop, I have 3 times more current because I have 3 times less voltage. So that voltage times current is a constant. So increase the voltage, decrease the current. Decrease the voltage, increase the current. All right, let's do a quick sample. So read the problem, start calculating. I will erase the board while you solve, although I always recommend you hit the pause button at this point in time. Don't let your cat hit the pause button because he's more likely, or she's more likely to just change it to another channel. And while that would be more interesting for anyone to watch than a physics lecture, it won't help you in this particular class. All right, welcome back from the other video that you spent 5 minutes watching when I mentioned something about switching channels and you did. Sorry, Nemesis is still not real. Okay. So let's solve. A, what is the power that is passed from the receiver to the light bulb? Boy, I may need to explain some of this, don't I? We call the receiver the first side, usually it's called that. So what is the power that passes through the first side to the light bulb? So in order to do this, we use power 1 equals power 2. And I know at this point you're thinking, but you didn't give us power 1. That means this is not a level 1 problem. This means it's a level 2 problem. So the first thing I need to do is calculate power 1. Power 1 equals current 1 times voltage 1. Let's see if I have that. Current 1 was 0.1 amps. Voltage 1, 120,000 volts, which means my power is 12,000 watts. Now I can solve for power 2. Power 2 equals power 1 equals 12,000 watts. Because once I solve for one side, I've got both sides when it comes to power. All right. Now I'll give you a pause moment to do the other two if you haven't done them because you got stuck on part A. All right, current from the light bulb. Power 2 equals current 2 times voltage 2. Oops, that one doesn't seem to work, does it? So let's try something different. Sometimes the first one you grab is not going to be the right one. That happens. So, I2 over I1 equals N1 over N2. I just inverted this equation over here. Since I1 over I2 is N2 over N1, that means that I2 over I1 is N1 over N2. Inverse. That means that I2 is equal to I1 times N1 over N2. N1 was 3,000 because it had more voltage. N2 is 3 because we have less voltage, times 0.1 amps. And this gives me 1,000 times 0.1, which is 100 amps. All right, part C. Voltage 2 over voltage 1 equals N2 over N1. I'll just now solve that for V2, like so. So I put the V first, just to be a little easier. 3 over 3,000. Because N1 was big and 2 was small. So I'm divided by 1,000. 120 volts. Now, if I take this times this, I should get 12,000. And in fact, I do. So that gives me a sanity check to make sure I did my math right. All right, so I'm thinking, okay, that seems straightforward enough. Now for the complicated stuff. All right, let's complicate this as much as I can. Done. Wait, that's the same slide. Oh, I guess that's as complicated as it gets. Now there's only one other thing to learn about transformers. The types of transformers. There are 2 types of transformers. Not Hollywood versus physics. 2 types of physics transformers, that is. And they both involve voltage. If your voltage goes up, meaning that V2 is greater than V1, so you go from low voltage to high voltage, you're increasing your voltage. Then you have a step-up transformer, because you're stepping up the voltage. If your voltage goes from high to low, so V1 is higher than V2, you're going down in voltage, then you have a step-down transformer, because you're stepping down the voltage. And that's as complicated as transformers get. Like I say, they're all that meets the eye. All right, to wrap up, we've learned about the flow of circuits, flow of current in circuits, both series and parallel. We learned how to calculate voltage and current in both series and parallel circuits, as well as the resistance. We've learned that choosing series or parallel allows us to fine-tune our current to different parts of the circuit. And if we don't like a voltage, we can always transform it. We learned something about power equals current times voltage, and voltage equals current times resistance somewhere in part 1. And that's all. All right, till next week. Enjoy your time.